Good day guys, let's get one more question on moment of inertia. So we'll go through it just as we've been doing. So this question says calculate the point of intersection of x squared equal to y squared. That's the first important thing. And x equal to y plus 2. Then sketch the two graphs and show the first quadrant area bounded by the graphs. It should be bounded by the graphs and the line y equal to 0. Show the strip that you use to calculate the volume generated, the volume of the solid generated when the bounded area rotates about the x-axis. So once I go through that question, that is the important information I see. So I'll now capture it down. So I've seen the equation x equal to y squared. That's equation number 1. I've seen x equal to y plus 2, equation number 2. Then I've also seen another equation, y equal to 0. Y equal to 0 is another name for the x-axis. Since on the x-axis, y is always 0. Then the other important pieces of information I've seen is that they are insisting on first quadrant area. So that is where you are putting your strip and shading that portion. And finally, they are also insisting on x-axis rotation, which tells you how your formula for volume starts. So guys, that's the important piece of information. So if we go back to the question, we need the point of intersection of the first two graphs. Then after that, we'll sketch all the three graphs and show the portion in the first quadrant surrounded by the three graphs. Then we'll put our strip in that portion. So let's go for point of intersection. If I substitute equation 1 into equation 2, what it's telling me is that I'll be having y squared is equal to y plus 2. To solve an equation, you must put everything on one side. So I'll get y squared minus y minus 2 equal to 0. That is a quadratic. You can solve it using the formula. You can use factorization. If it works, I'll try to see if factorization works. Let's see something like y plus 1 into y minus 2. Is it okay? That gives me y squared. Then minus 2y plus y, that gives me minus y minus 2. Yeah, so that's perfect for me. You can also use the quadratic formula to do that. You use factorization as I've done. And from here, you see that your y is equal to 1 or y is equal to 2. I will always advise that once you solve a quadratic like this, don't be in a rush. Verify whether, my answers are y equal to -1, not 1, y equal to -1 and y equal to 2. You can quickly verify whether your answers are correct by resubstituting there. If I put -1 squared, it's a 1. Negative times minus -1 is another 1. 1 plus 1 is 2. Minus 2 is 0. So this guy is correct. Then if I put 2 there, 2 squared is 4. Minus 2 is 0. So that one is also correct. So I can now get the corresponding x values. If I put y equal to 1 into any equation up there, it tells me that x is equal to 1. And if I put y equal to 2, I see that x is equal to 4. So therefore, my point of intersection are 1, -1, and the other one is 4, 2. So that is how it is. We can now go to our sketch. So to sketch the two graphs, if I've got points of intersection, they should give me a clue on where I should sketch my graph. So this one is in the first quadrant because all points are positive. This should be quadrant number 4 because x is positive, but y is negative. So that gives me an idea where my graph should be found. So if I'm sketching my graph, the quadrant I need is 1 and 4. So the x values are from 1 to 4, so I can just spread them out. 1, 2, 3, and 4. Those are my x values. get my 1 and 4 there. My y values, we've got a negative 1 and a 2. So I get something like that. This gives me an idea of what I should be expecting. So start by plotting my point of intersection. So I've got 1 and negative 1. My two graphs must meet here. Then I've also got 4 and 2. I've also made there. So now it's time to sketch the graphs. If you look at graph number 1 and 2, you can confirm that graph number 2 is a straight line. To draw a straight line, all you need is just a 2 point. I've already got 2 points and the point of intersection. So I will just link my 2 points to get my sketch. So my sketch is somewhere there. So that's my straight line. So I'm done with the straight line. Now if we need the next, what do? We check what kind of graph is that. That is a hyperbola. Sorry, it's parabola. I know we are familiar with the parabolas in the form y equal to ax squared plus bx plus c, which are either the smiling face or the sad face. So when you see something like that, that is also a parabola, which is the inverse of this parabola. This kind of parabolas in the form of x equal to ay squared plus by plus c, which are now moving like this for a negative, or like this for a positive. So these are things that N6 students are supposed to be familiar with. So if I look at this equation 1, I see that it is a parabola and the coefficient of y squared is a 1. That's a positive number. So I expect something like this passing through this point and through this point. Or better still, if you want to sketch a parabola, another thing is that you must get at least 3 points to be sure. So since I already have 2 points, I need another point. I just go there and say let y be 0. You see that x will also be 0. And it's reminding you that that parabola passes through the origin. So that is the shape, and I get it right there. So this is my parabola going like that. So I've sketched my graphs. So now we can go to the important story. So the important story here says we need to show the first quadrant area bounded by the graph and the line y equal to 0. Y equal to 0 is the x-axis. You can see the region between the two graphs spreads from the first quadrant to the fourth quadrant. But the question has made it very clear to you that we need the first quadrant area. So it means we are only settling for this one. The first quadrant area bounded by the graphs and the x-axis, which is also called the line y equal to 0. So that is how our diagram should look like. And from here, we can now put a strip inside. So there is little information about the limits because we don't have 4 graphs. But if you know how a strip operates, then you will still get it right. Because for you to get a perfect strip, make sure that when you put it in the shaded portion, you forever touch only the same 2 graphs. So if I try a vertical one, you see I'm touching these 2 graphs. These 2 graphs, that makes sense, but by the time I reach here, 1 graph has changed. This immediately eliminates a vertical strip for me. But if I go for a horizontal strip, you see whether I put it up there, or I go down to the center, or I go to the bottom, I keep on touching the same 2 graphs. So this makes a horizontal strip a perfect strip for my diagram. So I'll put it anywhere I want in this shaded portion. So that is my horizontal strip, which if I extend it, it touches the y-axis, reminding me that all the formulas I'm using in this equation, they must end with dy. And another thing it tells me is that my limit for any calculation I'm doing here must be right on the y-axis, where I started shading to where I stopped. So you see I stopped at 2, I started at 0. Then the last thing it tells me is that since my strip is horizontal, in line with the x-axis, the 2 graphs that my strip is touching must be labeled using x, as you already see in the equation. So all I need to do is know that the first graph is the one that is found on the right side of the strip. So that graph on the right side was my straight line, which is x equal to y plus 2. The second graph is the one found on the left side of the strip, which is my parabola. So that is it with the graph. So we are done with the A part. We can now go to the B part, which we are told to calculate the volume described in A above. So if I'm calculating my volume, the first point where I start is my rotation. My rotation tells me how my formula for volume will start. So x-axis rotation reminds me that my volume should be called Vx. Now, how does the volume end? I look at the strip in my diagram. See, a strip is touching the y-axis, telling you that my formula for volume ends with dy. So an N6 student will simply go to page 5 of the formula sheet. There is a topic there called volumes. Then you check for that volume that starts with Vx and ends with dy. The formula will be 2 pi, the integral from a to b of xy dy. If I want to accommodate the information on my graph, I will see x1 on the right side of the strip, x2 on the left. So I will simply capture it as x1 minus x2, all this multiplied by y dy. So that becomes my formula for my volume, which obviously it's the shell method. How do I know shell method? I see 2 pi outside. Another way I know it is that the strip in my diagram must be parallel to the axis of rotation. You see, the axis of rotation is the x-axis, the strip is parallel. Once the strip is perpendicular, it's the disk method. So this is the shell method. I can now start substituting. My A and B must be read from the y-axis, as the formula is saying, where you started shading to where you stopped shading, which is from 0 to 2. My x1 is see it as y plus 2. My x2 is y squared. Then I have to multiply this by y dy. If I open my bracket, I get 2 pi, the integral from 0 to 2. The y goes in to form y squared plus 2y minus y cubed dy. Then I do my integration. I get 2 pi. If I integrate y squared, I get 1/3 y cubed. If I integrate 2y, it gives me y squared. Or 2y squared over 2. If I integrate y cubed, I'll get 1/4 y to the power 4 from 0 to 2. Then I can substitute my limit, starting from the upper limit, that is 1/3 into 2 cubed plus 2 squared minus 1/4 of 2 to the power 4. Then the lower limit, it's a 0 plus a 0 minus a 0, since I'm using 0 everywhere it's y. So I will then use my calculator to do the calculations there. 2 cubed, you are 8. Times 1/3, that gives me 1/8/3. Then 2 squared, you are 4, so I'm adding 4 to that. Then minus 2 to the power 4, you are 16. 16/4, it's a 4, so it's minus 4. So I get 8/3, then times 2 pi. That gives me 16/3 pi. So that's my volume. My volume Vx is equal to 16/3 pi unit cube. So that's how we get our volume. So from our volume, we can now go to our moment of inertia. After our volume, we can now check our moment of inertia. So, moment of inertia, the definition starts from the rotation. Our rotation is the x-axis rotation. So if we go to page 6 of our N6 formula sheet, to copy the general formula for moment of inertia, I touch on x there to remind us that we are dealing with x-axis rotation. Then the general formula is the integral from a to b, r squared dm, which continues as density, the integral from a to b, r squared dv. Then our job is to develop this formula using the information we have. So to develop this formula, we need to check the kind of volume. Unfortunately, here we have the shell method. If it was the disk method, I'll simply go under circular lamina on page 6 of my formula sheet and copy the formula for Ix. But now that it's shell method, I must develop this formula. What I'm simply doing is that in the position of dV, which is an element of volume. I'm recopying the whole of my volume formula. So my volume formula has 2 pi outside. If I combine it with moment of inertia, you see there's density outside. So if I combine that, I'll get 2 pi density, the integral from A to B. Then inside, I'll leave space for R. Then I copy what is there, which is x1 minus x2 times y dy. Then now to get my R, I go back to my graph. I start from the center of my strip and move in a straight line to the x-axis. So we'll go to our graph and do that. So this is our graph with our horizontal strip. So if I start from the center of my strip, that's the definition of R. I move in a straight line till I get to the x-axis. So if you look at that movement, you see it's a vertical movement. Once I use a vertical movement, I describe my R using y. So this R, it's a simple y. So if I go back to my formula, in the place of R, I'm putting y. Therefore, R squared becomes a y squared. So that's how simple it is to get R. Then I can start replacing my A, B, C, x1 and x2. So I've got 2 pi. My A and B is the same A and B I use for volume, that's 0 to 2. Now, don't forget that here, what we're now seeing is y cubed, because we've got y squared times y, that becomes y cubed. Your x1 and x2 are the same things you see on your graph. Your x1 was y plus 2 minus your x2, which was y squared dy. Then I'll open the bracket to allow y cubed to go in. So I get the integral from 0 to 2. If you multiply this, you get y to the power 4 plus 2y cubed minus y to the power 5 dy. Then we'll go on and integrate. We'll get 1 over 5 y to the power 5 plus 2 over 4 y to the power 4. When we integrate that, minus 1 over 6 y to the power 6. From 0 to 2, then we'll substitute our limit. So we'll get 1 over 5 into 2 to the power 5 plus 2 over 4, it's like 1 over 2 into 2 to the power 4 minus 1 over 6 into 2 to the power 6. Then the lower limit, it's simply a 0 plus a 0 minus a 0, since we're putting 0 everywhere. So it's now time to consult the calculator to see what that gives us. So I'll concentrate only on the upper limit, since the lower limit is a 0. So 2 to the power 5, you got 32, so I get 32 over 5, then plus 2 to the power 4 is 16, 16 times a half is 8, then minus 2 to the power 6 is 64, so I get 64 over 6, so that is what I get. Then I multiply this by 2 pi, that gives me 112 over 15 density pi. So my moment of inertia, I said it's 112 over 15 density pi. So I hope that's what I got. Yeah, 112 over 15 density pi. So that's my moment of inertia that I've written there. So we can now look at the last part, assuming that we didn't make any mistake. The last part says we should calculate, or we should express our answer in C above in terms of the mass. So that means we are expressing the same answer we got in C in terms of the mass. So usually when doing that, we need to go to page 5 of our formula sheet to see the relationship between mass, density and volume. And from there, if you make density the subject, you will see that you get mass over volume, reminding you that if you want to write this moment of inertia in terms of the mass, you simply take your moment of inertia, you divide by the mass, by the volume, sorry, since the volume is being divided there, then times the mass. So that's basically what we're going to do. So our moment of inertia, I'll copy it without the density since it's been replaced by mass or volume. So I'll put in 112 pi over 15. I divide this by my volume. My volume was 16 pi over 3. Then I multiply this by m. So and then consult my calculator to see what it's telling me. So in my calculator, I know that when I do this division, pi will cancel pi. So I'm simply taking 112 over 15 and divide by 16 over 3. So divide by 16 over 3. That gives me 7 over 5 m. So this is 7 over 5 m. If you like your answer in decimals, it's still fine. That will give you 1,4 m. So, ladies and gentlemen, this is how we get our moment of inertia and express our answer in terms of the mass. Thank you very much.